Okay, awesome. So once again, thank you very much for the invitation. Today I will talk about visual question answering on remote sensing images. Let's see if this works. Yes. Yeah. So first I would like to take you to a trip that I did recently to Italy, to Benevento, where I really love the place. It's a small city in Italy. And before I went there, I was asking myself some questions. I wanted to know a bit where I was going. So, for instance, I did what I think most people would do, which is to go on Google Maps, maybe put the satellite images, the satellite view. We love satellite images. And I asked myself some questions. For instance, oh, that looks like a monument. And I want to know its name because I want to go and see it. Okay, I want to know a bit about its history. So this one is named Arco di Traiano. And then I might be interested in knowing a bit more about the urban characteristics of where I'm going. So for instance, I would like to know how many buildings are there in this area. Or if I dezoom a bit, if I look at a bit wider area, still want to know the number of buildings, but this starts to be a bit complicated. So here it would be 672. And for instance, as I am a tourist, I might be interested in knowing where to go, which places are nice to visit. So to ask for an itinerary going through the main monuments, which could look like something like this. And finally, if I really love the place and I want to have a secondary house there, maybe I want to know a bit about the urbanization policies of where I'm going. For instance, I really don't like modern flats, so I might be interested in knowing where they are not building modern flats. So for instance, which area had the least new buildings in the past 10 years? And it could tell me like this area, for instance. And these are the questions I am interested in when I visit a new city. But I'm sure, because we are all different, when you visit a different city, because you have different tastes, you might be interested in different things. So you might have different questions. And my assumption is that everybody is interested in the environment, whether it's because they care about it, and so they want to protect the environment, they want to know about the environment, or just because you want to travel to the other part of the other end of the world, and you want to enjoy your touristic visits. And to answer these questions today, it is a bit complicated. So, for instance, this looks like a monument. What's its name? If you remember this question, that's quite easy. You just go to Google Maps, you click on the monument, and it will give you the name, a link to the Wikipedia page. Okay, that's easy. But to ask for an itinerary going through the main monuments, that's a bit more complicated. Okay, you will use Google Maps, but you will need to create a script that would find find the different monuments, that would compute an itinerary. It starts to be a bit more complicated. How many buildings are there in this picture? We had this question. We have several options. Either we have a shapefile of the place, and then we can do a simple automatic counting of the number of shapes, vector data in the shapefile, or we need to build a segmentation model and count. Okay, that starts to be really more complicated. And finally, the last question that I had, I fell in love with the city and want to buy a flat. Which area had the least new buildings in the past 10 years? That starts to be really complicated. You need to load a time series of high resolution images because you want to be able to see construction, to segment the different buildings, to do change detection, which just to answer this simple question is way too much. We don't want to have to do that, and probably not many people will do that unless they really want to buy an expensive flat. So again, everybody is interested in its environment, but even for me, and I assume you, because you are all working in Earth observation, it is difficult. I have knowledge in GIS, I have knowledge in AI models to extract information from your data, but it's difficult to do to answer this kind of questions. So, of course, for the other people, it's the people who don't have the technical knowledge, is basically impossible today. That's why we went with the task of, we proposed the task of visual question answering for remote sensing, where basically the goal is to build models which from an image, as you can see here, and a natural language question, so for instance in English, we'll try to predict an answer also in natural language. This is a task that we proposed back in, so the first publication on that was in 2019, when I was a postdoc student. But the idea of visual question answering came from a bit earlier. So the first trace that we can find is from 2014, where Jeman and Jeman, who you might know because they enabled the use of Markov random fields in image processing back in 1984, so 20 years before that, 30 years, sorry, before that, they proposed a visual equivalent to the widely known Turing tests. So they thought, okay, Turing tests are becoming, like, it is becoming for machines to be possible to pass or to be close to passing Turing tests when it's about natural language interactions. What about images? And this is kind of what we would be tackling here. In terms of visual question answering per se, the task in itself, it came for the first time in Vision in 2015. So we are celebrating the 10 years of this paper actually this month. And back then, they had built a very big data set of images and associated questions and also answers with questions such as this one. So for instance, what is a mustache made of? Okay, here it would be banana. So they took 200,000 images from MS Coco, which is an object detection data set, and they used a tool called Amazon Mechanical Turk, where basically it's an interface to real humans that will actually do real annotations to build 760,000 questions and 10 answers per question. So if each of these answers were collected from different people, and they had this big data set that we could work with in computer vision, but with natural images. And the first potential application, because you could ask yourself, and that's actually what a lot of people were asking back then, the first potential application came in 2018 with VisWiz, which is a challenge that was built for visually impaired people. So the idea was to ask visually impaired people to work with a camera and that they could take pictures or movies about their environment and ask questions to the system. So for instance, yes, this one I like, they set the temperature of the oven on, and they want to know at which temperature is it. And indeed, for someone who doesn't see well, it can be very difficult. And such a system which could answer automatically to question about images would be very useful in this case. And in 2020, we made the first big publication about this task in remote sensing. And since then, in the past 5 years, there were a lot of follow-up publication on the task. Here I put a selection of the ones that I might talk about today. I will not talk about everything, don't worry. But first, I will talk about this one. Let's start with the basics. Don't hesitate to interrupt me during the talk if there are questions. Let's make it interactive. If let's not stick with the question at the end. So if there are questions, don't hesitate to raise your hand or to unmute to ask them. So for this task to be done, we have to look at two things. First, we have to collect some data, because of course we are going to use machine learning models that will learn from data So we need to first collect data. We also need this data to evaluate our models once we have them. And then we'll have to build some models which can solve the task. But first, let's look at the data. So as I said, we need this data to evaluate our model, to train our machine learning models. And data for visual question answering looks like that. We have one image, one question, and one ground truth answer, so a triplet. So for instance, here we have an image. Is there a park in this image? And the answer would be yes, because indeed we have a park in the top left of the image. So I had a look about what was possible in 2018. There was no such data set, of course, in remote sensing because it was a totally new task. So we looked at what we could do. And the first option was to do like the VQA papers that we just saw before. So to go on Amazon Mechanical Turk, which is super nice because it's real people who would ask questions that they care about and other people who will answer these questions. So it will be kind of realistic of what someone could do, but it's very costly. So I made a calculation that it would cost us about $100,000 to build 80,000 questions and the associated answers. And it's very hard to extend, and it costs to extend. So for instance, if I realize that 80,000 questions is not enough, I need to pay twice to have 160,000 questions. And I was a postdoc at that time, so I asked my supervisor, Davis Truya, if we, by any chance, had $100,000, sorry, somewhere that we could spare on this task. And he told me that's what I was costing for about a year. So he asked me, either we do that and we don't pay you, or you find another solution. And since I like being paid, we found a different solution. So the different solution is to base ourselves on existing data. So for instance, OpenStreetMap. If we're able to derive questions from OpenStreetMap, sure, it will be less representative from users' needs because I will be the only one generating questions from OpenStreetMap. So it might not represent what everybody might be interested in. But there's still a manual component to it because OpenStreetMap has been filled by human. So it is reliable. There is a manual component to it. And the big advantage is that it's free. And because it's free, if I can derive questions from OpenStreetMap, we can generate as many questions as we want. So we are not limited by money to build our data set. So the general idea that we had to generate this data from OpenStreetMap was in two steps. First, we are going to generate a lot of questions which we can answer using only data that is present in OpenStreetMap. And once we have built these questions, we are going to answer the question on specific images. That's what we want at the end, these image triplets, image question answers. So let's look at the first step, generate a question which we can answer with the same data. Again, at this point, we are not looking at images. We are just trying to generate a lot of questions. So we look at all of the different elements that were present in OpenStreetMap. Of course, we have a lot of them. So for instance, roads, buildings, this kind of thing. We don't have non-permanent objects such as cars, pedestrians, this kind of thing. So we are limited to a specific set of objects. But we have all of these objects available. And let's start with one. So for instance, here a religious place. And then we can add attributes to our objects. So for instance, because we have the shapefile, we can look at the shape of the objects that we selected. So here I might be interested in circular religious places. We can build relations with other objects. So for instance, positional relations, so buildings above a circular religious place. And finally, we can ask specific questions. So we can ask counting question, comparison question, presence question, and rural urban question. That's what we started with. But here I will take a comparison question, which would give the following question. Is there more buildings above a circular religious place than roads? And we just need to add a few words to make it really a question. So The final question that we generated in this case is there more buildings above a circular reduced place than roads in the image? But you see that through that, because it's a stochastic process, we selected randomly some elements, we can generate almost an infinite amount of questions. Once we have questions, of course, we need to find the answer for a specific image. So let's look at this second step. We still this question, is there more buildings above a circular reduced place than roads in the image? But let's look at now a real image. So for instance, here it's in Amsterdam. And we look at the OpenStreetMap data corresponding to this geographical extent. And we are going to take the same question tree that we built at the previous step. So first, we were interested in religious places. And here we can see that in this image, we have two religious places, this one and this one. I hope you can see my mouse. I'm not sure. Can someone tell me if you see my mouse?
Yes, I can see another.
Awesome.
Yeah. It's moving, yeah.
Yeah, great. So we have the two religious places. Then we said that we are interested in circular religious places. So the only circular religious place that is left is this one. And we wanted the buildings that are above a circular religious place. So we look at all of the buildings and we select the ones that are above. And finally, we wanted to make a comparison between the number of buildings above the circular religious place and the number of roads. And so we can answer the question, just looking at the shapefile data from OpenStreetMap. So if we look at what we have been doing until now, we know how to generate almost an infinite number of questions, and we know for each of these questions and a given image how to generate the answer just looking at OSM data. We are not looking at the image, we are just looking at the OSM data corresponding to the geographical extent of the image. We can do that for many images, and like that, simply get a data set. And that's what we did. First, we started with Sentinel-2 images. So we took 772 Sentinel-2 images, such as this one, and we built 77 question and answer. So close to the 80 questions that we had in mind before, and that would have cost $100,000. So an example of question in this image is, what is the number of water areas? 7. That would be the answer in the ground truth. We also built a higher resolution dataset with 10,000 very high resolution images at 15 centimeter resolution. And we built close to 1 million question and answer. So again, this would have cost more than $1 million to build. We got that for free. And again, another example, what is the amount of buildings in this image? And the answer is also 7 in this case. I will stick to this one for the rest of this presentation and just show you a bit how it works. So the images were acquired at the east coast of the USA, so mostly in the area of New York. But we got 10,000 images that we got from 161 large VHR images, and we built 2 test sets. So as you can see, we have in red the samples that are in the training set, in green the one in the validation set, and in blue the one in the test set. So we had mixed test sets in terms of geographical location. We had a few training examples in the city of Portland, but we also did a second test set in the city of Philadelphia, which is testing how much the model is able, if we train it on just the cities of New York and Portland, how much is it able to generalize to a non-seen city during the training? So in this case, Philadelphia. In this dataset, we had 4 question types. So the presence, a specific object, the comparison, is there more of these objects than the other, counting how many of these objects are there, and area, what is the area covered by objects of this type. And we got the following distribution of questions. So you have the 4 types of questions in the inside of the chart, And outside of the pie chart, you have the distribution of answers. So we can see that in terms of questions, we are relatively balanced. We have more or less as many counting questions as presence question, and a bit more comparison question, but it's still kind of manageable. However, when we look at the answers, it is absolutely not balanced. When we look at presence and comparison question, indeed, it is kind of balanced. We have a bit more no than yes. This is natural. We ask questions a bit randomly about the images. So most of the time, a specific object will not be present. So for instance, if I ask, is there a road in this image, and I take random images from different places, most of the time there will not be a road, so the answer will be no, a bit more frequently. But when we look at number questions, so for instance, counting, I didn't put the label because they are really easy to guess once I tell you the behavior of the answers. For counting, we have more than 50% of the answer which are 0. Again, if you ask how many roads are there in this image, if there are no roads, the answer will be 0. So most of the time, the answer will be 0. And then we have 1, 2, 3, and basically it's a heavy tail distribution. A bit the same for area questions, but we defined 5 ranges. So 0 square meter is still the majority one, but then between 1 and 10 square meter, between 10 square meter and 100 square meter, between 100 and 1,000 square meter, and finally more than 1,000 square meters. But the fact that we have an unbalanced data set makes it very hard for us and to train models, because when you train from unbalanced data, you have issues in your models afterwards. But we'll see that later during the presentation. Let me jump to the model part of our work. So we have these triplets of image, question, and answer. Both the image and the question are input to our model. And let's look at how we will process each of these information. So first we have the image, and our goal is to obtain a feature vector, which is an abstract representation of the image that will contain information that is essential to answer the question. So for that, we need a visual feature extractor, and we use something very simple, which is a simple ResNet, a CNN, that was pre-trained on ImageNet. And that's it. We simply use a CNN, and we get the corresponding feature vector from our image. Then from the question, to process the question and again obtain a feature vector at the end, we need a text feature extractor, and what we used is a recurrent neural network. At the time, transformers were already existing, but not so prevalent as they are now. So we had a question as an input, and basically each token of the question will go through a fully connected layer to predict a hidden state vector. And then, starting from the second word, we will predict a new hidden state vector from both the token, the second word, and the previous hidden representation. And so we do that recurrently, and at the end, we have a feature vector. In our case, we did a bidirectional recurrent neural network, so you do the same, but reading from the end to the beginning. And we can put a fully connected layer again through all of this. For instance, here it would have been trained on translating. So we have the question in English, we would translate in French, and we obtain. So in our case, sorry, it has been trained on masked word modeling. So you mask a word, and basically the model is trained to reconstruct the word. So for instance, here, there, if you don't give this word, what you would like is that when the model sees something, a park in the image, it predicts that something is there. So this bidirectional LSTM was pre-trained on book corpus with this masked modeling, and we take the last feature vector predicted by our model, and this one will be the feature vector representing the question. So at this point, we have two feature vectors, one that represents the image, one that represents the question. Next, we would like to take these two feature vectors and make them one. We want to merge this information. There are a lot of possibilities to merge the information, so that's fusion. But what we did is to project both feature vector to a lower dimension using a simple fully connected layer again. And then we have what we did is simply to take each dimension of our vectors and to do a pointwise multiplication to fill our merge vector. So a simple pointwise multiplication between two vectors that have nothing in common. It's a bit weird, but we'll see that it works. So that's our fusion step. So at this point, we have one feature vector that represents both the image and the question. And finally, the last step is to do the prediction of the answer. You have two types of models. The first ones are the easiest ones. They will classify among a set of predefined answers. That is, that we'll look at a set of all possible answers, and we'll try to predict the most probable one. The second approach is open-ended generative answer. So that's what you see with LLMs such as ChatGPT, for instance, where we try to predict a sentence. In the end, it's also a task of classification of words, but just that it's autoregressive, which is not our case here, because we went with a classification of among a set of predefined answers. So we look at all of the possible answers for the questions that we had, and we try to predict the most probable one. So for instance, we have yes, no, 0, and we just use a simple multi-layer perceptron to do this prediction. And that gives us classification scores, and that's it. That's our model. So once we train it, what we hope is that when you give this image and the question as an input, you will get the output, yes, there is a park in this image. And you can compare that to the ground truth that we obtained through OpenStreetMap and through backpropagation, train our model. When we apply that to the high resolution datasets that we saw earlier, we get this type of scores. So these are the different types of questions, and we look first at the first test set, the one that was in domain. That is that we had training data from also New York cities, and we are going to test in New York City. So for counting, we got 68% of accuracy. That means that in 68% of the cases, our model was answering the right answer. We also looked at standard deviation by training several models, and then we can look at the different performances between the models, but we can see that overall it's quite stable. For presence questions, we had 90% of accuracy. So when you ask, is there a park in this image, for instance, that is a presence question, 90% of the time our model will give the right answer. In terms of comparison, 88%, and when we look at areas questions, we're at 85% of accuracy. Let's look now at what happens when we change the city. So the problem is a bit harder because you might agree that a building in New York City might not look exactly the same as a building in Philadelphia. So we are making the problem a bit harder, and we get this type of scores. So overall, we get 5 to 10% of lower scores. And when we look at the average of all of these scores, it's 83% for the first test set. So in 83% of the cases, we will give the right answer, and 77% for the second test set. And when we look at the weighted average, so the overall accuracy, we are at 83%, still for the first test set, but 78% for the second one. One nice feature about our model is that even when it does not give the right answer, as you can see in this confusion matrix, it gives an answer that makes sense. So for instance, if you ask again, is there a park in this image? It might tell you yes instead of no, but it will not answer 0 to is there a park in this image. So still the answer makes sense most of the time. That's what you can see with the red boxes, which group the answer by answer types. So all of the yes, no, areas, numbers. So let's look at some qualitative results. So for instance, is there a residential building at the bottom of the place of worship? The ground truth was yes, and the prediction in this case is yes. Because indeed we see the cross here that gives us the fact that we have a place of worship, and we can see a part of building. So the model is quite efficient at detecting these kind of things. And there are some interesting results that were surprising to us. So for instance, in this case, what is the amount of large buildings? Unfortunately, you all have your camera turned off, so I will not be able to make a poll about that. But I would like that you make the exercise yourself and try to answer this question. So when I show this example and I ask the room to vote, I have about half of the rooms that will vote for the fact that there are 3 buildings and half of the rooms that will vote for the fact that there is 1 building. And indeed, like these buildings, they might be considered as 1 building or 3 different buildings. We cannot really know. And what is funny is that in our case, the ground truth was saying 3, which means that the 3 parts of the building were registered as separate buildings in OpenStreetMap, but our prediction was 1. So our model considered that this was 1 single building. It's wrong, but it makes sense. So it shows that it's a bit an ill-posed problem. I will go through a bit. So that's it for this first paper. Are there questions at this point?
Yes. Yeah, any questions, please? I have one question, Sylvia. So the models that you have used for feature extractions for both text and images, it seems they are based LSTM and also for conventional layer methods. So what is your rationale that you have chosen this model? Because a lot of time people in natural language processing field, they speak about the other models like vision transformers. I think in the time that you started the project, maybe it was the best choice for this. But if you want to start now, do you start with vision transformers or the same model you use? And what is your rationale for the choice of your models? Yeah, definitely. So thank you for the great question. Definitely, the choice was motivated by the fact that it was at the time the best possible model. Again, transformers, they really appeared in 2018. I started working on that at the end of 2017. So it was just not there. So we couldn't choose them. And back then, ResNet and bidirectional LSTM were kind of the best choices that we could make. So, and I presented it at the bidirectional LSTM. If you want, like the truth, it's a model called the skipsat vector, which is based on LSTM, but it's a bit too complicated to explain in 2 minutes like I did for LSTM. So I simplify it as an LSTM, but it's a bit more advanced than that. Yeah. Okay, thank you very much. And my next question is that because your model seems to limit themselves by some certain questions like counting or presence or area. So is it only limited to these questions, or are you free to ask other questions, or how it works? If you want to have, can you fine tune your models to add new questions? Yeah. So at that time, we tried to do that. Of course, we had this model that was capable of answering questions, and we thought, let's try to ask weird questions, completely out of the domain of these questions, and it completely failed. So 0 accuracy if you go outside of this domain. Of course, now using, and I will show some example of that, using a bit more advanced methods, we are capable of getting better models, of course. Yeah. Okay. Thank you very much. Thank you.
Yeah, I have a question as well.
Yeah.
Yeah. So you said even when it might give the wrong answer, it still gives answers that make sense. Could you please backtrack to that? I was just trying to understand really what that meant.
So, for instance, these are all in the confusion matrix. So you have here the prediction, here the ground truth. And in the confusion matrix, you can see that when the ground truth answer is 0, you will basically, in 99.9% of the time, give an answer that is in this red box. So that's this line. So when the answer is 0, you will, in the majority of the cases, that's why it's darker, you will answer 0. But in other cases, you will answer 1, 2, 3. But you will almost never answer yes, no, 0 square meter, or this kind of thing. So it means that if I ask how many something, the answer might be 0, might be 1, might be 2, but it will not be yes, which was something that we were a bit afraid of, because then it really doesn't make sense. And as we could see in the visual, in the visual example here, like in this case, the answer is wrong, sure, but it's also kind of right, according to a lot of people. Yeah. And that's also because it gives an answer that makes sense. So that's what we were checking in this confusion matrix. It's not necessarily the right answer, but it makes sense semantically.
Okay. Thank you.
Yeah, thank you. Awesome. Thank you for the questions. I will continue to a bit more recent works because we and other labs did a lot of things around that. And I will first look at what people have been doing on the side of data, and again, what people have been doing on the side of model. So in terms of data, there are several things that were not great with what we did at first. Again, we were the first one to do it. We had no idea of what we were doing, and we just tried to put something out so people could start working on it. But it is complicated to produce a high-quality data set, and so definitely what we did was not the best quality ever. And there are several reasons for that. So, for instance, the fact that it was very limited to, in terms of geographical extent, it was just some very specific part, very urban part of the East US coast. We, as Vahid asked for the question, we had a very limited diversity in the amount of questions, that in the types of questions that we could ask to the model. And you might be interested also in, because we are doing Earth observation and we have the chance of having a lot of different modalities at our disposal, which can give different information, we can try to go multimodal. And I will insist a bit on that because I understood that some of you are doing SAR. So we, of course, I did SAR during my PhD quite a lot. I love SAR, so we try to work with SAR for this task. And again, this is better balancing. I will start with the geographical and question diversity quickly. So in our case, we had one that was the east coast of the US, one that was the Netherlands, but both are quite small. And once we had this data set, we thought, okay, can we try to do something a bit better? So the data sets were ready towards the end of 2019. And we looked at what was available in remote sensing, in Earth observation, in terms of data sets in 2019. That's what we had. That was the main data sets, according to a review that I found for 2019, that were available back then. I don't know how many of you are working on large deep learning models, but you know that now we have new data sets almost every day with often hundreds of thousands or even millions of images that are available. So back then we just had less than 10 data sets that each had less than 40,000 images. So that was really small scales. And already with RSVQA HR, with 1 million, close to 1 million questions and answers, we were quite like large scale in this sense. One data set that arrived, and which was ERC topic of Begum, was BigEarthNet. So BigEarthNet, it's a data set that links Sentinel-2 images, such as this one, with queried land cover labels. So for instance, here, we have this queried land cover, which is a European project, which makes the land cover at the scale of EU, and we we can know that in this image we have discontinuous urban fabric, non-irrigated arable land, and so on. And BigGovNet made a huge data set from this data. So linked these two data and made a huge data set. And again, that's complicated because that was the topic of an ERC. So we had the idea with Davis, with Begum, to work on a new dataset that would be called RSVQA meets Ben, BigGovNet, where we exploit this dataset to try to build a new one. So for instance, if you have this image and this set of labels of land covers that are present in the image, if you ask a question about land covers, so for instance, is there a broadleaf forest? You can answer just looking at the labels. So we could build a ground truth just looking at the label. In this case, we have broadleaf forest in the list of labels associated to this image, so we can have the answer yes. And similarly, we can ask about a different land cover. Is there a permanently irrigated land? We can see that permanently irrigated land is not in the list of land covers for this image, so the answer would be no. Okay, so we built this data set, which took from BigGovNet about close to 600,000 images and built 15 million of question and answer, and it was covering most of Europe. So that's good because we have a much better geographical diversity. We are at a very big region of the world now, and we can ask different questions, logical questions, which, so for instance, we can ask, is there a forest and a water area in this image? And both need to be present to answer yes. And this was a first step toward reasoning for a model. And so we built this data set. I will not show results for now, but basically, since the initial proposition of our datasets, the 3 datasets that I talked about in 2020, many people build some datasets with sometimes very different questions. So for instance, FloodNet is a dataset that had been built specifically for flooded areas. So you will have questions such as, is there a flood in this image? What is the condition of the roads in this image? These kind of things. So new type of questions. We can also try to add modalities so capabilities to our models. So for instance, modalities. And that's what we did with one of my PhD students, Lucrezia Tosato, who will actually defend her PhD next week. I'm very excited about that. And one of her first studies was this one, SARS Strikes Back, A New Hope for RSVQA, which she found the title, I found it very funny. And she saw that we had this BigGovNet dataset. I bought this RSVQA meets BigGovNet dataset. But in the meantime, the team in Berlin who was behind BigGovNet built BigGovNet multimodal. BigGovNet multimodal was associating the Sentinel-1 images corresponding to the Sentinel-2 images in the dataset. So we thought, okay, let's take the questions that we already have about Sentinel-2 and see if when we add Sentinel-1 to the model, it helps to answer the questions. So this is RSVQA meets BigGovNet multimodal. Again, I will not show the results yet. I will show them when we'll talk about the models. But we went a bit further afterwards with 2 of my PhD students, Isham Boussaid and Lucrezia again. And we tried to go a bit more in front in terms of multimodal. So let's take this image. So if I give you this image, some of you might recognize that it's in Paris. Maybe if you know a bit how Paris looks like, but it's a bit complicated. However, if I show you this image, I guess that more of you would recognize it's Paris just because, for instance, we can see the Eiffel Tower here. we can see Champ de Mars, we can see a lot of things corresponding to Paris. So our assumption is that very high resolution images, such as this one, are nice to answer questions about small, very localized features. But it's also nice to have the context and the multispectrality of Sentinel-2, for instance. And of course, we might want also to have the SAR data to get structural information about the buildings, in the end, maybe exploit the different polarimetric capabilities of SAR, and so on. So we built this data set, which combines orthophotos, very high resolution, again, 15 centimeters, about a place, and a larger multispectral area. So the white box that you can see here corresponds to the geographical extent of the VHR data. So we have a larger Sentinel-2 data, but also we put SAR data. And again, because the resolution of that we selected for Sentinel-1 in this case was 5 by 20 meters, the box becomes a rectangle. And on this type of question, you would be able images. Sorry, you would be able to ask questions such as: is this area prone to flooding? To which department does the area in the image belongs to? So the answer would be Paris, as we saw earlier. But we have different parts of France covered with that. There were also some work, for instance, by the team in Munich, Xiao Shangsu, about change detection, visual question answering. So ask question about changes. So you have an example. What are the regions of buildings in the pre-event image, which is here, mainly change 2, and the buildings that were in the pre-event image mostly change to low vegetation. That's what we can see here. So this, which was a building, became low vegetation. And finally, a final reason why we want to build new data is better balancing. I have a confession to make. I have shown you great results earlier with our first model, but what we knew back then, it's actually written in the paper. There was no lie involved. But what we knew back then is that we had these results, that looked very nice. So in 83% of the cases, when you get the image and the question associated to it, you got the right answer. But we had an idea to try to change the image for a random one. So you agree that in most cases, if we change the image to another image, the answer to the question should be very different. So for instance, here, what is the amount of building? It's not at all 7 anymore. It would be, in this case, 0. But what we saw is that when we were putting a random image, our model was still right 70% of the case, which is problematic. That's way too high for a random image. If just imagine you ask a question about a random image, like you can, without seeing the image, you cannot provide the answer. So here, the model was not seeing the real image and still able to answer correctly. And this is because the language biases. I've shown you earlier what we had as distribution in our dataset, but let's look a bit more precisely in the low resolution dataset for counting. We saw that it was a heavy tail distribution. So this is in log scale, but even in log scale, we can see that the huge majority of the time we ask how many of an object is there, the huge majority of the time, the answer would be 0. And therefore, if our model, when it doesn't know, answers 0 to the question how many whatever, it would be right a majority of the time. It will have more than 50% of the counting question right just by answering always 0, which is not what we want, because it's a useless model, a model that would always answer the same thing. So one of my PhD students, Christelle Chapuis, who is here, made this huge study about language bias in the current state of the art of RSVQA, visual question answering. And basically what we saw when we look at the HR dataset that I've shown earlier is that we have this table. So these are the question types. These are the number of samples in the test set for each question type. And these are the number of possible answers. So for instance, we have present questions. There are two possible answers. It can be yes or no, with the most common answer being no. And as you can see, no, 0 square meter is always the most common answer. And then she computed different metrics. So for instance, the score you could get by learning the biases at question type. So that is a model that would recognize that you have an area question. And as soon as it sees an area question, it will answer 0 square meter. In this case, it will get 62% of area questions right. And overall, here, 63% of the question right. This is the score you get when answering randomly. So you have, in this case, for instance, five possible answers, because we have the ranges 0, 1 to 10 square meter, 10 to 100 square meter. So if you select one of the possible answers randomly, you will get 20% of right answer. Basically, what we would like is to have this score as low as possible, or at least as close as possible to this one. So we made a formula to evaluate how close are we at the dataset level in these two scores. We would like that a model that learns the biases does not better than a model that does not learn the biases, in which way there would be no biases in the dataset. Basically, we can do a dataset score and compare the different datasets and try when we publish a new dataset to see if we have biases in our dataset. She also provided metrics to evaluate the performances of the model, taking into account the biases. So in this case, we just report how much better than biases are we doing. And finally, I will not talk about it too much because it's not out yet, but we have the checkmate dataset that is coming soon, where basically we have a new dataset where we try to make visual question answering interpretable, that is to understand what's happening inside the model to provide the answer, and explainable, which is that the answer also provides an explanation of why they answer this specific answer. Okay, let's look a tiny bit about the models. Yeah, we'll try to be a bit fast. We have, this is what the framework that we saw earlier. And let's look, for instance, at the visual feature extractor. We have two properties that we would like to ensure for the visual feature extractor. First, it should be adapted to the resolution and the modalities that we have at hand. So some people have been trying to work on that because that was not the case in my initial proposition. It was just a vanilla ResNet. And you can also work at the scale of objects, that is to first detect objects in the image and to work on them. That's what this team in Australia did based on formulations that is called LXMERT, or with transformers. Again, so that was a question of Baid. Then a bit later, after we started this project, some people have been working with transformer to tackle the task. And they should extract relevant feature for the question. And because we also need to see the text to understand what is relevant for the question, we'll tackle that in the fusion part. For the text feature extractor, we did some studies on what are the best practices. Again, we did that, I think, in 2021. So back then we had transformers available, and we saw that transformers are helpful instead of a simple recurrent neural network as we saw earlier, but they are also much more prone to biases. So transformers are more powerful. I'm talking about simple transformers, not large language models. They can be helpful, but they're also much more susceptible to biases. Then for fusion, the main area of improvement that people have been working on is fusion. Based on what I said, that we want to extract features that are relevant, image features that are relevant for the question. And this means that ideally, we'll have, so remember, we had this pointwise multiplication between the two vectors. Ideally, what we would like to have between the two vectors is more of a quadratic, so it's more the multiplication of one vector by the transpose of the other one, which has the problem of being quadratic. That is that this vector will be at the end the square of the dimension of this vector. And this is a big problem because these vectors are at the scale of 1,000 elements. So we would have about 1 million dimension in our feature vector representing both the image and the question. And this 1 million element would need to be at the start of an MLP. So quickly, it will become like billion of parameters models, which are not possible to train with the data that we have in Earth observation. So we cannot do that. What we are doing earlier is a pointwise multiplication, which corresponds to taking the diagonal of this matrix. A second solution that was proposed is to do an algorithm that is called MCP, count sketch projection. Basically, you shake this first feature vector, and you will mix some elements of this feature vector. So for instance, you will take this one minus this one, and you will put in the first dimension. And then you will take this one minus this one plus this one, and you will put it in the second dimension. Looks weird, but it allows to take into account more dimension at once. And then we do, again, a convolution between these two vectors, and we obtain one feature vector representing both modalities. A third proposition, which looks like attention in a way, is the Tucker decomposition between the two feature vectors to obtain one final feature vector, which is actually repeated r times. And we sum them to get the output of our Tucker decomposition. This will allow more interaction at lower dimensionalities. These last two solutions, solution number 2, the MCP, and the Tucker decomposition, you can see them as type of attention mechanisms that got super popular indeed with transformers, and which would help to extract feature relevant for the question. So we had this study as well, which tackled that. And finally, for the prediction, as we said, we want to do a classification from a set of predefined answers. We look at all of the possible answers. We try to classify the most probable one. But this does not work at all well with numerical answer, because with numerical answer, so if you ask how many buildings are there in the image, it is more of a regression task rather than classification task. You would like to penalize more your model when the model will reply 10 instead of 100, rather than if it replies 10 instead of 11. And with classification, you will give the same penalization to both because they are completely different classes, whereas if you tackle that as a regression problem, you will get better results, hopefully. So to do this, we took the MLPs that we got. Yes, so that's what I was explaining. We have, for instance, the question, what is the number of buildings? 42. At the end, if we have the answer 42, we would like that it's less penalized if we have the answer 43 rather than the answer 12. So what we would like to be able to do is to use a regression loss, so for instance, mean square error, on numerical predictions. To do that, we took our feature vector representing both the image and the question, and we try first to classify what type of question is it. Is it a classification question, for instance, presence comparison, or is it a regression question? So for instance, area or counting question. If it's a classification question, we just give our feature vector to a classification branch that will do the classification. So if the goal is to predict yes or no, we will go through this branch. If the goal, sorry, it's not segmentation here, it's regression. If the goal is to do regression, we will predict a single number and then apply regression loss on this path. So basically, we have two heads that predicts the relevant answer based on the question type. So this was a paper that we published, I think, back in 21. And if you remember, I talked about the second approach, which was open-ended answers with autoregressive models. So instead of predicting just one class, we are trying to predict a sentence. People have started to do that. So for instance, Google in 2024, in their Polygemma model, they also tested it on visual question answering for remote sensing. So they had a model that worked on a lot of different data, but they did some experiments on all datasets. So RSVQA, low resolution and high resolution. And when I saw these results, I was astonished. They got close to 93% on the two main test sets in low resolution. And at that time, the best model were at 89%. Remember, our first model was at 83%, and last summer, the best model were at 89%. So I was really like, this is a huge leap forward to gain 3% at once. What I saw is that they use only the questions that were not about numerical answers, both for low resolution and high resolution, which is not very honest because, as I don't know if you remember, but what we saw earlier is that the counting questions are the questions that our model struggles the most on. So they removed this part which was difficult for their model, and they were able to claim very high results. But so also, these type of models are not good with counting. That's the main difficulty right now. Okay, I will not talk about data augmentation. I will just keep this to try to conclude quickly. And let's continue with a new type of model that is completely different from what we have seen before. That's the last type of model that I will show, where basically, in this case, we wanted to take advantage. So it was in we started to do this study in 21. And even though ChatGPT didn't exist yet, we knew that large language models were existing and were working great. So we wanted to take advantage of that. And we thought, okay, how can we use these large language models? And basically, our answer was to convert the image to a textual description. So we use a visual feature extractor to do a textual description of the image. And to do that, we simply do a multi-level classification to classify the different objects that are present in the image. And then once you take a text feature extractor that will take the question, but also the image, you can get a feature vector that represents both the question and image. So basically, we put the heavy lifting on the text feature extractor only. And finally, you can put against this feature vector to a prediction head and get your output. This is what we called prompt RSVQA, which was presented at the Earth Vision workshop of CVPR in 22. And the nice thing about that is that we have better interpretability because we have a textual description of the image and an answer as an output. We can see if we don't have the answer that we expected, we can understand through the textual description of the image if the answer is wrong because the textual description of the image was wrong, in which case the problem lays in the visual feature extraction, or if the natural language model was wrong. So we can understand a bit better what's happening here. The nice thing is that this approach can also be adapted with vision language models that appeared a bit later. And that's what Christel did in the Pan RSVQA paper. Finally, that's also what we had in the Checkmate papers that I talked about before, which we use a prompt-based framework to have the interpretability, and in addition, we predict which part of the visual information was useful to answer the question. So that's it for the models, and that will conclude my presentation. I just want to give some path forward for the task of visual question answering, because we still have the issue, and we saw with, for instance, the big foundation model of Google Panigema, which is still not able to treat numerical answers well. So we still have this issue on numerical answers. Multimodality is not solved. We recently published, so it was over the summer at, again, a workshop at CVPR. We recently published a model that uses the TAMI dataset that I presented earlier with the VHR S2 and S1. But there are still a lot of work to do on multimodality. There is also a lot of work to do on time series. So almost none of the models that I've shown you today is capable of handling time series. And as Vahid recognized earlier, we are very restricted in the type of questions that we can ask. I think these models will have value once they will be able to answer questions on things that remote sensing is already used for. So for instance, agriculture, hydrology, this kind of thing. And finally, we are working on our side, in my team, on foundation models, and in particular, vision language foundation model, because we truly believe that this is the next path forward to get better visual question answering systems. So I'd like to thank you all for attending this presentation. I would like to thank you, the different PhD students and postdocs that worked with me in the past 5 years, but also the supervisor, and in particular the ones who worked on this task with me. So we have Lucrezia, Hisham, and Christel, the PhD student who worked on that. Thank you very much. Do you have questions on this presentation? I cannot hear you, Vahid. I don't know if
okay. Yes, I have a question, but I think you answered it in last PowerPoint, but I just try to clarify your what I understand. So when you say that foundation models, are you aiming to have a foundation models for visual question answering? Because in your one of your work that you said that you have created millions of questions for remote sensing data. Do you think that by having this in the future, or maybe your future works, we can fine-tune for any different specific application? For example, I'm interested in detecting something, or like ships or whatever in the data, but then I'm able to use those foundation models for visual question answers of your data set for my own case, like fine-tune it for any specific application?
Yes, that's really what we want to achieve, because like I think these two questions, typical remote sensing questions. So for instance, ship detection would be also a typical remote sensing application, and foundation models are very linked. I believe that we will not be able to achieve, because I've been working on that over the past 7 years, a bit more than 7 years now, almost 8. And I see with the evolution of datasets that we are not able to reliably build big datasets for specific applications, and all of the specific applications that different remote sensing practitioners are interested in. Foundation models, through self-supervised learning, they are able to have an internal understanding of these different applications that we could be interested in, and then they can be fine-tuned to different downstream tasks. I think visual question answering will stay a downstream task, a possible application of these foundation models. But we are now working on foundation models that we plan to apply on visual question answering, but also other things. And we hope that by going one step above with foundation models, we'll be able to have visual question answering models that are able to answer much broader questions. And that's what we are starting to see, actually.
Okay, very interesting. Thank you very much. And I have one more question. In terms of the modalities that you have used, let's say that you have got orthophotos data or Sentinel-1, Sentinel-2. Each of them could have different resolutions. It could be in different times, or it could be different characteristics, spectral differences. I mean, for Sentinel-2, and the radar has got its own characteristics. Maybe one image has got, when you ask how many buildings, maybe because of the radar geometry, it has got like 5 buildings, but in Sentinel-2 we have got 6 buildings. How you trust which answer is correct for depending on your modality? How you correct that?
So that's actually, So we didn't look at that specifically for visual question answering, but we looked at that for foundation models with the idea that indeed the modalities are providing complementary information about the scene. One modality will give you specific information about a characteristic of the scene, and other modality about different characteristic. And so we are trying to model the uncertainties about the different modalities when we build our visual feature representation. I just wanted to show also, for instance, I think your question was because of the SAR geometry projection, right? The fact that
I mean, because the SAR has different geometry, and you can see the buildings, with a different angle than optical. That looks from the nadir angle. So it might be we have cases that we might not get the similar exact number of buildings, for example, looking at the different sensors. So
when we thought about that, we had 2 possible solutions. The first one was to go to ground range detected data, GRD data, which would kind of remove this issue, but I really don't like that. Because we are losing all of the useful statistics of SAR. So our solution is to work with the context. Basically, in the TAMI dataset, all of the questions are about the part that you see in white, which represents the extent of this image. So in the SAR data, we took a lot of margin. All of that is margin, which will allow the fact that, for instance, if you have a large building that would be in the center of the image, sure, I don't know where is the sensor in this image, but sure, maybe it would be projected in range somewhere here, the end of the building, on the left of this white box. But because we took some margin, and the question is only about what is inside of the white box in both Sentinel-2 and Sentinel-1 data, we hope that the geometry will not be too much of an issue. It is an issue from what we can see in very mountainous areas, but in general, it's not so much of an issue.
Okay, very good. Yes, any other questions? Thank you very much for your answer. It was very fruitful talk so far. Do we have other questions? Okay, so if not, I think Sylvia, even so, we have, we have promised to have hands-on exercise. Maybe it's a little bit,
it was too late,
have just booked for 1 hour. Maybe we can do it later on when you have time for this.
Yes,
so
what I would propose. what I would propose is that I will share with you what I had planned to do. So this is, if you go to this link, you have 3 exercises. I would suggest to stick to number 2, which is the most interested one. And basically, there are few. I can share this screen.
I just stopped recording here.
So if you go